Hi everyone, in this video I've got a pretty challenging physics problem for us to have a look at. We're going to find the effective resistance of this resistor network that I've sketched out, which is made up of many repeating units built out of 1 ohm resistors. So the repeating unit that I'm talking about is this part of the circuit that I've just highlighted, where you've got a 1 ohm resistor along that wire at the top, and then a 1 ohm resistor connecting the wire at the top to the wire at the bottom. So I've said that there are n repeating units, where n is just an arbitrary positive integer. As it turns out, this problem is fairly straightforward to solve if n is infinite. That was something that I talked about in my last video, but it turns out to be much more mathematically involved to handle the case of finite n. So we need, of course, to set up an equation for Rn, which is what I'm calling the effective resistance of this network. And the first observation I want to make towards setting up that equation is that you can view Rn as the resistance of the entire network from the far left end all the way to the far right end, wherever that is. Of course, depends on how many repeating units we have. So I'm just going to draw that arrow at the top and label it as Rn. Whereas if you were to ignore that first repeating unit and start measuring your resistance from this point, which I'm now marking at the top of the diagram, that would be related to Rn, but you would only have n minus 1 repeating units, and so that would be Rn minus 1. And just that observation already sort of pushes us in the direction of setting up a recurrence relation for Rn in terms of Rn minus 1. So what's that relation going to be? Well, we can use our rules for combining resistances in series and parallel to write down what Rn is in terms of Rn minus 1. So firstly, you notice that you have a 1 ohm resistor, so you always have at least 1 ohm in your Rn expression. Then you've got the more complicated bit, which is sort of everything from this point to the right. So essentially what you have is this 1 ohm resistor in parallel with everything to the right of that 1 ohm resistor. So it's a 1 ohm resistor in parallel with effectively a resistor of resistance Rn minus 1. Now, of course, when you have things in parallel, you add the reciprocals of the resistances, and so the effective resistance of that parallel combination is going to be 1 over, and then the denominator, you're going to have 1 over 1 plus 1 over Rn minus 1. You can get rid of the nested fractions, specifically this 1 over Rn minus 1, by multiplying the top and bottom of that big fraction by Rn minus 1. And so the right hand side just becomes 1 plus Rn minus 1 over Rn minus 1 plus 1. And then we can combine the entire right hand side into a single fraction by writing this 1 as Rn minus 1 plus 1 over Rn minus 1 plus 1. And so the recurrence relation becomes Rn equals, you're going to have 2 Rn minus 1 plus 1. And then the denominator, of course, is still Rn minus 1 plus 1. Now, this recurrence relation might not look too bad at first glance, but then you recognize that it's non-linear, and that actually makes things pretty challenging to deal with. So there are a couple of approaches we can take to solving this. The approach I'm going to take involves assuming a particular form for the solution Rn. So I'm going to say, let's let Rn be equal to some fraction, Pn divided by Qn. Why is that a reasonable thing to do? Well, the recurrence relation itself is a fraction, and so it's reasonable to assume that we can write Rn as a fraction and solve separately for its numerator and its denominator. As to why that's actually helpful, well, we'll see in a couple of steps' time. First of all, the left-hand side of our recurrence relation is just Rn, the left-hand side is now just Pn over Qn. The right-hand side, well, instead of Rn minus 1, you're going to have Pn minus 1 over Qn minus 1. You still got that plus 1 on the numerator, and then the denominator is almost the same, but without that factor of 2. So Pn minus 1 over Qn minus 1 plus 1. And then you can again deal with the nested fractions on the right-hand side by multiplying everything by Qn minus 1. So it becomes 2 Pn minus 1 plus Qn minus 1 divided by Pn minus 1 plus Qn minus 1. So if this fraction on the left-hand side is supposed to equal this fraction on the right-hand side, what's the implication of that? Well, you can actually get two equations, one from equating the numerators and one from equating the denominators. More precisely, you can say Pn is proportional to, in other words, it's a multiple, let's say, k times the numerator on the right-hand side. So Pn is k times 2Pn minus 1 plus Qn minus 1. And the denominator of the left-hand side, Qn, also has to be proportional to the denominator of the right hand side, and that constant of proportionality should be the same. So you're going to have k pn minus 1 plus qn minus 1. Why do those k's have to be the same? Well, when you divide these two equations by each other, you will see that the k's cancel as long as they're the same, and you recover the original recurrence relation from the line above. If the k's were different, then you'd have an extra constant of proportionality that wasn't there in the first place. We can, however, make an even further simplification and just say that k is equal to 1. So I'm going to say, let's set k equal to 1, and we can do that without loss of generality. The reason is that you don't actually care about the values of Pn and Qn individually. All you actually care about is the value of Rn, the actual resistance, which is the ratio of Pn to Qn. So when we've solved for Pn and Qn, we're going to eventually divide them by each other, and then whatever k we chose, it would just cancel out at the end. So we may as well set it to be 1 from the beginning, just to make the algebra a little bit easier. So what was the point of introducing p and q in the first place? Well, it's because we've now transformed our original nonlinear recurrence relation into two coupled linear recurrence relations, the Pn and Qn equations in terms of Pn minus 1 and Qn minus 1. When you've got two coupled linear equations, you can solve them using linear algebra, and so it would be helpful to rewrite those two equations in matrix form. So let's make a vector out of Pn and Qn like that. Right, the left-hand side is just Pn, Qn. Remembering that we set k equal to 1, our matrix of coefficients of Pn minus 1 and Qn minus 1 is going to be 2, 1 from that top equation, and then 1, 1, the coefficients from the equation at the bottom. And we're going to have that matrix multiplied by Pn minus 1, Qn minus 1. For ease of notation, let's give that matrix a name. Let's just call it A. And so we can then just write that as A multiplied by the vector Pn minus 1, Qn minus 1. Now, because n is arbitrary, it follows that the relationship between Pn and Pn minus 1 must be the same as the relationship between Pn minus 1 and the term before that, which was, of course, Pn minus 2. So if you wanted to write this equation in terms of Pn minus 2 and Qn minus 2, you would still have your A, but then you'd pick up an extra factor of A, because this vector here is A times the equivalent vector, but with n minus 2 instead of n minus 1. So you could write that as A squared multiplied by Pn minus 2, Qn minus 2, and you could keep going as far as you wanted until you reach P1 and Q1. And by the time you reach P1 and Q1, you will have accumulated n minus 1 lots of the A matrix. So you're going to have A to the power of n minus 1 times P1 and Q1, which are the first terms in those two sequences. Now, do we know what P1 and Q1 are? Well, remember the definitions of P and Q were that you get the resistance of n repeating units by dividing Pn by Qn. So we need the resistance of just one repeating unit. One repeating unit is just, remember, this part of the circuit here, and it's just two resistors in series. And so R1 is just 2. You can write 2 as a fraction, 2 over 1. Of course, there are other possible choices, but the simplest possible choice is just 2 over 1. And so you can take P1 to be 2 and Q1 to be 1. And therefore, Pn Qn can be written as A to the power of n minus 1 times the vector 2, 1. So just to summarize what we know so far, we've said that Rn takes the form Pn divided by Qn. We've said that Pn and Qn satisfy this matrix equation involving the n minus 1th power of the matrix A, where we derived that the matrix A was this thing 2, 1, 1, 1. So now we've basically reduced the problem to finding the n minus 1th power of that matrix. So we need to spend a fair bit of time thinking about how to come up with an expression in terms of n for A to the power of n minus 1. So often the best way to take powers of a matrix involves this mathematical technique called diagonalization of a matrix, which makes use of the result that I've quoted at the top right, D equals S inverse times A times S. So in brief, what does this mean? It means that you can construct the matrix D, the diagonal matrix, as defined here, lambda 1, 0, 0, lambda 2, where lambda 1 and lambda 2 are the eigenvalues of the matrix A. I'm saying that there are two eigenvalues because it's a 2 by 2 matrix. And to get from A to D, what you need to do is construct the matrix S, where the matrix S has columns which are the same as the eigenvectors of the matrix A. Then you find the inverse of the matrix S. You do the inverse matrix times A itself times S, and that is going to be equal to the matrix D. If you've never come across that idea before, then that equation I quoted is going to look a little bit strange, and you might be wondering where it's come from. It's a pretty standard result, though. I'm not going to prove it here. I'm sure there are plenty of sources where you can read up more about that. I would like to cover that in a future video, but that's kind of getting into a whole other topic. So you'll have to trust me that this works. Now, what does this actually have to do with finding powers of a matrix? Well, you take that relationship D equals S inverse AS, pre-multiply both sides by S and post-multiply both sides by S inverse, then you get A on its own, and you conclude that A is equal to S times D times S inverse. If you then raise both sides of that equation to the power of n minus 1, you get A to the n minus 1 equals, let's write it like this, SD S inverse multiplied by another SD S inverse multiplied by another SD S inverse, and so on, until you get n minus 1 copies of SD S inverse, because that's what the power of n minus 1 means. So now you have to notice that you're going to have a bunch of S minus 1 S's sort of sandwiched in between the D's in that equation, and S inverse times S, by definition of inverse, is the identity matrix, and therefore S inverse S doesn't do anything. So you're going to still have your S at the beginning of that equation, so you've got an S there, but then you're just going to have a bunch of D matrices and n minus 1 of them to be precise, so D to the power of n minus 1, and you've still got that S inverse at the end. Now this is useful because the conclusion is that A to the power of n minus 1 is the S matrix multiplied by the nth power, or the n minus 1th power of a diagonal matrix, because D was this, remember, and taking the nth power of a diagonal matrix is easy because you just raise each entry along the diagonal to that power. So it's going to be the first eigenvalue, lambda 1 to the power of n minus 1, still 0 there, still 0 there, and lambda 2 to the power of n minus 1 there. And of course, you've still got your S inverse matrix at the end. If you didn't know that rule about how to take powers of diagonal matrices, you can prove it yourself pretty quickly just by using the general rule for matrix multiplication. So that's the point of diagonalization in this context. That's why it helps us, because it's easy to raise an eigenvalue to a power because it's just a scalar, whereas it's not easy to raise the matrix 2, 1, 1, 1 to a power. So of course, if we want to make use of this, we have to actually find the eigenvalues and eigenvectors of A, and we can use the standard procedure. So we take the determinant of A minus lambda I and set it equal to 0, where lambda is at the moment just a generic eigenvalue. So what that means is you take your A matrix, subtract lambda from each of the diagonal elements, and then take the determinant of the resulting matrix. So you're going to get 2 minus lambda in the top left entry, so 2 minus lambda. The lower right entry is going to be 1 minus lambda. Multiply those, subtract off 1 times 1 minus 1, and set that equal to 0. That is going to expand to give you a quadratic equation, of course, because you've got lambda times lambda, lambda squared minus 3 lambda plus 1 is equal to 0. And then you can easily use your favorite method for solving quadratics to show that you get two solutions. I'm going to label them as lambda plus and lambda minus, and they are 3 plus or minus the square root of 5 divided by 2. Note, by the way, that originally I called the eigenvalues lambda 1 and lambda 2. Now I'm switching to calling them lambda plus and lambda minus, because that way it's easier to keep track of which is which, because they only differ by that sign in the middle. So now we've got the two eigenvalues, we need to find the eigenvectors as well. So to do that, we of course solve the equation ax equals lambda x, where lambda is an eigenvalue because that's the definition of an eigenvector. A is 2, 1, 1, 1. Let's write our eigenvector x in component form as just x, y, just any two arbitrary letters. And then on the right hand side, we multiply the vector x by an eigenvalue. I'm going to do both in one. So instead of just writing lambda, I'm going to write lambda plus or minus, so we can take care of both at the same time, multiplied by x, and then lambda plus or minus multiplied by y. At this point, you have a choice whether to form an equation using the elements at the top or the elements of the bottom of the vectors on the left-hand side and right-hand side. Doesn't really matter. I think the elements at the bottom give you a slightly easier equation here. So I'm going to do 1, 1 times xy, which gives you x plus y, on the right hand side, the lower component is just lambda plus or minus multiplied by y, and you can rearrange that to get x in terms of y. So x is just lambda plus or minus 1 multiplied by y. So for each eigenvalue, lambda plus and lambda minus, we know how the x component of the corresponding eigenvector is related to the y component. So we can construct some eigenvectors and put them into this S matrix, which remember was the matrix whose columns are the eigenvectors of A. So we can write down that S is equal to, and we've got to keep the eigenvectors in the same order as the eigenvalues. So we can do lambda plus first and lambda minus second. If we say that the y component of the first eigenvector is just 1, then that very straightforwardly tells us the x component corresponding to that is lambda plus minus 1. Then the second eigenvector, let's again just take the y component as 1. The x component is of course then going to be lambda minus 1. There's the S matrix. So thinking back to that equation at the top, we now know S, but we also need S inverse to plug in there. So let's go through our standard procedure for finding the inverse of a matrix. To know the inverse, we have to first find the determinant. So we do lambda plus minus 1 times 1, which is just lambda plus minus 1. Then we subtract lambda minus 1 times 1. The ones cancel, you just get lambda plus minus lambda minus. And from those definitions there of the lambdas, it follows that this difference in the determinant is equal to root 5. Then we construct the inverse, s to the minus 1. You do 1 over the determinant. Then if we call the original matrix A, B, C, D, it goes D minus B minus C, A. So we swap the diagonal elements. We get 1 there, and we switch the sign of the off diagonal elements. So the next component is going to be minus all of that stuff, lambda minus 1. That's a minus sign there. And this 1 at the bottom left becomes negative, and then we have our lambda plus minus 1 at the bottom right there. So then you can construct this huge equation that's just appeared at the bottom there, which has just come from subbing in S and S inverse to the equation at the very top. So I've just had to clear a bit of space because our equations are getting pretty long, but we've got all the information we need on the screen, and we've now reduced our problem to basically doing this, which is evaluating the product of 3 square matrices. We're going to do everything in terms of lambda plus and lambda minus, which are defined here, remember, because I think that's easier than just subbing in the actual values at this stage. Now, multiplying square matrices when you've got algebraic expressions like the ones that we've got here is not very hard, but it's pretty time consuming, and I don't think it would make for a very exciting video for you to watch me going through all the algebra. So I've done the multiplication of those 3 matrices. You may find it a fun exercise to do it yourself as well, and make sure you get the same thing that I did. I'm pretty sure I've written all of those pluses and minuses correctly, although it can be hard to keep track of them all. So how do we convert that into Pn and Qn? Well, you use this relationship up here. So I can turn the left-hand side of this equation into Pn, Qn, and all I have to do is multiply that big matrix by the column vector 2, 1. When you do that, things tidy up a little bit, as you can see in this column vector here. You can collect together some like terms which were previously in different elements of the matrix after you do the multiplication. Now again, the algebra itself is easy but not that exciting, so I don't think you want to watch me go through all of that, but it might be useful to try it yourself. What I will do is point out 3 relationships involving the lambdas that I found useful from this point onwards. First of all, it is very straightforward to prove that lambda plus or minus to the power of minus 1 is lambda minus or plus. In other words, lambda plus to the minus 1 is lambda minus, and vice versa. You can prove that just by doing 1 over the actual number that you know lambda plus or minus is equal to, and that's useful to know because those powers of minus 1 appear in our column vector there. Secondly, it's useful to know what 1 minus lambda plus or minus is equal to, because you've got those 1 minus terms there. Again, just because you know the values of lambda plus or minus, substitute that in and you conclude that 1 minus that is minus 1 minus or plus the square root of 5 divided by 2. And another very helpful identity is 3 minus lambda plus or minus. You can see that's going to be really useful because you've got 3 minus the lambdas all over the place in that column vector. If you do 3 minus this thing over here, you will conclude that that's equal to lambda minus or plus. So because of the way that those numbers work out, doing 3 minus one of them just gets you the other one. I found making use of those three identities to be the most pain-free way of writing the column vector in terms of actual numbers. When you've done that, of course, all you need to do is take the x component, which is Pn, and divide it by the y component, because that's the definition of Rn, right? It is Pn divided by Qn. Now, there are a couple of equivalent ways to write your final answer for Rn, but I settled on this expression down here. That looks quite nice to me. Now, one thing I want to point out that I find quite interesting about this expression is that Rn should be a rational number because it's just a combination of 1 ohm resistors. But of course, our nth term expression contains irrational numbers because you've got those root 5s all over the place. So it works out in such a way that the irrational parts of that nth term cancel out in just the right way to make sure we always have a rational number. The final thing I would like to do is consider the limit of this expression as n tends to infinity, so that we can sort of check our answer against the more commonly known version of this problem, which is also the version that I covered in my last video. So if we let n go to infinity, what is going to happen to Rn? Well, the way to do this is to just keep the dominant terms on both the top and bottom of the fraction. Now, what do I mean by dominant term? Well, 3 plus root 5 is, of course, a number that's bigger than 1. Now, as it turns out, 3 minus root 5 is less than 1. So as you raise 3 plus root 5 to larger and larger powers, it gets bigger and bigger. As you raise 3 minus root 5 to bigger and bigger powers, it keeps getting smaller and smaller. And so it's the second term on the numerator that dominates. So as n gets really big, the top tends towards just minus, and then 1 minus root 5, and then 3 plus the square root of 5 to the power of n minus 1. By exactly the same logic, it's the first term, this one here, that dominates on the denominator. So we keep the 4 brackets 3 plus the square root of 5 to the power of n. Then you can divide the top and bottom by 3 plus root 5 to the power of n, which is nice because it makes all the n dependence disappear. So you get root 5 minus 1, flipping the signs because there's a minus sign in front of the whole thing. Then you've got 1 power of 3 plus root 5 left over, and then the whole thing is just over 4. You expand the brackets, and then the third part is going to be 3 root 5 minus root 5, which is 2 root 5, and the non-third part is going to be minus 3 plus 5, which is 2, so you've got a plus 2. The whole thing is divided by 4. Then you can, of course, cancel down a 2 and get 1 plus root 5 divided by 2, which is commonly known as the golden ratio and given the symbol phi. So even though Rn for finite n is always rational, the limit in the case of infinite n is actually irrational. And reassuringly, this result is also consistent with what we derived last time using a much easier method. For me, solving this problem was particularly interesting because the maths involved was a little bit unexpected. When I set out to find the resistance of a circuit, I didn't expect that I would end up diagonalizing a matrix. So thanks for joining me, and I will see you again soon.